Hi everybody. First of all, I would like to thank the people from H2Tech Solutions for giving us the opportunity to present our project here with you today. Our project is called the BenortH2 project, and it will be Spain's first green hydrogen plant, coming online in late 2022. My name is Kieran Power. I'm the General Manager of Bizkaia Energía, one of the investors in this project. Bizkaia Energía is a 785 megawatt combined cycle gas turbine based in the northern region of Spain, close to the French border. Joining me today will be Sergio Reyoso of the New Technology Business Unit of Sener, who has been named as our engineering contractor and is also an investor in the project. When you look at this project, you think, why Bizkaia Energía? Clearly, for all of us here today, decarbonisation is a key goal. Due to the project's location, we're near local industrial facilities, which opens up markets to us for green hydrogen. We've also got access to a highway, which allows us to ship and transport green hydrogen to customers. Finally, we have got access to a gas network, which allows us to inject green hydrogen into the gas network, serving more customers and clients, both industrial and domestic. On site, we've got a ready-made infrastructure, an electric substation, a grid connection through which we can import green energy, and also a supply of water. We are also supported very ably by our O&M staff, a team of 45 people who have been with the project for 18 years. Again, when you look at Bizkaia Energía, you can see that our site is quite an ample site. We have got room here for storage, for fuel cells, for gas pipelines, for electrolyzers, and also for injecting hydrogen into our gas turbines. You can also see that we have the substation already built and commissioned, allowing us to import green electricity for the electrolyzers. This solid basis of good infrastructure gives the project a head start compared to many other projects and means that we will be the first project generating and creating green hydrogen in Spain by the end of 2022. Looking at the consortium itself, the lead company on the consortium is White Summit Capital. White Summit Capital is a shareholder in Bizkaia Energía and also in Nortegas, the local gas network operator. CCI is the major shareholder of Bizkaia Energía. Nortegas is the main gas network supplier for the whole region of northern Spain. And as I've previously mentioned, Sener is our local EPC contractor and a company who was involved in the original construction of the Bizkaia Energía power plant. The vision of this project is in line with the European Union's goals for 2030. Primarily amongst those is the goal of decarbonisation. A second goal is digitalisation, and in that regard, our project will run with a digital twin, which will allow us to constantly monitor the progress and ensure that the processes are as effective and as efficient as possible. It will also aim at targeting social development, preserving existing jobs and creating new quality employment jobs as the Basque region moves to become the green hydrogen corridor for Spain. Looking at the process, we see this project being split into two phases. Phase 1, between now and the end of 2022, will see 20 megawatts of hydrogen electrolyzers being installed. This will generate 2,000 tons of hydrogen per year, and 12,000 tons of CO2 will be abated as a consequence. By 2030, the project will have increased to 200 megawatts, generating 20,000 tons of hydrogen per year and displacing 120,000 tons of carbon dioxide. In terms of investment, behalf of the shareholders, phase 1 will cost 50 million euros, whilst phase 2 will cost 300 million euros. As you can see, whereas in the technical criteria, the scalability is linear and logical, when you look at the investment, you can see that the investment sums are not linear. This is because during phase 1, we plan to install the technology, infrastructure, engineering, control, and all the other works that are necessary to make sure that the project can be scaled from 20 to 200 megawatts without any further engineering requirements. Looking at how the process works. The first part of the process is green hydrogen. We get green hydrogen by using electricity that comes through a 400 kV system and comes either with power purchase agreements or with green certificates of origin. You can see this in the green tower. After that, this electricity goes to the electrolyzers. The electrolyzers are stored below our air-cooled condenser, where we have a significant amount of space available and is easily scalable up. You can see also the green tanks, which is where our supply of water comes for the electrolyzers. This green hydrogen that is generated can then be stored at a pressure of 300 bar. You can see beside the electricity network where the storage system will be located. With the green hydrogen, we have several options. The first and most logical option is to inject it into our gas turbines, which we can do at a percentage of 3% hydrogen to 97% methane. With the gas turbines we currently have, which are General Electric 9FA technology, this hydrogen can be injected straight into the gas turbines without the need for any modifications to the gas turbines or the gas turbine hardware. Higher injection rates of up to 18% can also be achieved with the same gas turbines, although some of the hardware would need to be modified for this to be the case. We're also looking at a fuel cell. You can see the fuel cell here to the right of the graphic. The fuel cell will be charged up with the green hydrogen and then used to discharge electricity to the system to protect the system and cover the system as it may need frequency coverage or voltage control in the future, thereby providing a very vital system protection role. As it's a combined cycle gas turbine power station, we have access to a gas pipeline. Our plan here would be to inject at a percentage of 5% hydrogen with a 95% methane into the BenortH2 network. The BenortH2 network supplies industrial and domestic customers in the north of Spain. Currently, the injection limit is 5% hydrogen to 95%. In the future, however, we believe that this limit will be changed and relaxed, allowing us to inject up to 20% hydrogen into the gas network. Conversations with the regulatory authorities are ongoing in this regard and are moving quite smoothly. As I've mentioned previously, the power station is near a motorway highway exit. For this reason, we intend and plan to install a hydrogen refueling station, and we are in conversation with local public and private transport companies to ensure that they can pull in right beside the power station, charge up their buses and head off again. The initial stage of the process are the ones identified here: gas turbines, hydrogen fuel cell, gas pipeline, and a hydrogen refueling station. And with that, I will hand you over to my colleague, Sergio, who will take us through the engineering design, the digital twin, and the search for the lowest cost of hydrogen. Thank you very much. I hope you enjoy the rest of the presentation. Goodbye.
Thank you, Kieran, for your kind introduction, and thanks as well to H2Tech for giving us the opportunity of presenting to you this amazing project. And good afternoon to everybody. Thanks for being here. Okay, so on the design of the plant, we have to say that this is a complex problem. Complex because we have three parameters to determine, which are the electrolyzer power, the storage capacity, and the operation strategy. Operation strategy meaning when and how much hydrogen we're going to produce, store, and inject to the different consumers. But we're in a complex scenario. We have complex boundary conditions. Electricity first is important because we need cheap electricity to produce the hydrogen, but we are looking for high prices when we inject the electricity from hydrogen through the gas turbines or the fuel cell into the grid. But the electricity pool price is going to vary a lot. From January to December, you see here a representation of the electricity pool price in the year 2020. Varies a lot, as you can see, from one month to the other one, and also throughout the day. Normally, we have two peaks of price in electricity, early morning and late afternoon. Okay. On the other hand, with the consumers being the major consumer, the natural gas pipeline, we're going to inject here approximately 80% of the hydrogen produced in the phase one. So the problem is that the current legislation allows us to up to a 5%, okay, in hydrogen content with respect to the natural gas flow through the pipeline. The problem is that the natural gas flow is varying a lot from winter to summer. Okay, in winter is much higher than in summer, and also throughout the day we have variation. So the question is, what is the perfect combination of electrolyzer power and storage capacity that leads to the lowest cost of hydrogen, which is what we are looking for eventually? Well, it's a complex problem, so we calculate all the design alternatives. What we have done is to combine the whole design range of the electrolyzer power here and the whole design range of storage capacity. And for all these combinations, we have calculated the CapEx, the production, and the OpEx. With these three parameters, we can calculate easily the levelized cost of hydrogen of each alternative. So the design of the plant is the optimum, the economical optimum, okay? Is the alternative with the lowest cost of hydrogen, thanks to the calculation of all the alternatives. This is the philosophy. Okay, about the digitalization of the plant, for us is mandatory. I mean, as you have seen, it's going to be a complex problem when to purchase electricity, when to inject into the gas pipeline, when to send it to the gas turbine, okay, in conjunction with the operation of the plant to sell the electricity from hydrogen at a higher cost, okay? So it's a complex operation, and we know perfectly that this has to be automatic. I mean, we cannot charge an operator, a person, I mean, operating the plant with the responsibility of selecting the best way or the best moment in which to start up the electrolyzers or charge the storage or discharge. I mean, it's going to be complex and it has to be automatic. And also, we are looking for the maximum profitability of the project. So we know perfectly that all this has to be automated. To help us with the operation of the plant and the automatization of the whole process, okay, we're going to implement a digital twin. A digital twin is not only a model of your plant receiving the signals, okay, from all the sensors in your plant. A digital twin is a combination, okay, of three things. You have to have a model of the plant, okay, and you have to have received all the signals from the plant, so you are monitoring the operation of the plant, but you are giving this digital twin certain capacities of advanced analytics first, then simulation capacities and artificial intelligence. So in a way that the digital twin is going to help us to operate the plant and to predict what is going to happen with the electrolyzers, okay, in terms of I mean, maintenance or schedule outages of of the plant, okay? Just to engage this maintenance of the electrolyzers and the rest of the facilities with the scheduled maintenance of the combined cycle plant, okay? So digital twin is going to allow us, in summary, to fully integrate the operation and the monitoring of this green hydrogen plant into the combined cycle plant. And this is going to lead us to an increase in efficiency of the plant and to fulfill the cost of hydrogen that we are looking for, that we are targeting, okay? On the location of the plant, this is exceptional in our opinion, because the combined cycle of Amorebieta is located in the center on the Biscay province here in Spain, in the north of Spain, as you can see, okay? And we have different advantages here, okay? First of all, and for me is the principle, is that since we're going to export approximately the 80% of the consumption through the pipeline, it's very convenient that we have the network, the gas network of BenortH2 very close to the plant, okay? And this is going to help us to easily export this hydrogen, which is going to be, as I said, the main consumer, okay? Also, I mean, it's a very well industrially developed region here in Spain, the one in which we are located, and we have a quick access to a highway, okay? And we have also very quick access to the shipping port of Bilbao, which has a very large volume of import and export of goods, okay? And also, and as Chiara mentioned at the beginning of the presentation, we have an industrial network of clients, okay, which can be potential consumers for this H2. I mean, small and medium scale facilities which are going to need this hydrogen in the short to medium term. So exceptional location for the project together with the maturity, let's say, of the combined cycle of Amorebieta. And as a summary, okay, just some points to highlight the you know, the strongest features of this project. Well, first of all, and as Karen said at the beginning, we're aiming at the Q4 2022 or Q1 2023, okay, to produce hydrogen at a commercial scale. We have a very strong partnership in the project. We have, let's say, investment partners, i.e. White Summit Capital and CCI, okay? And on the other side, we have, let's say, the energy and engineering partners, okay? We have Vizcaya Energía, which is the owner of the plant. We have BenortH2, which is one of the major players in gas industry in this country. And also we have Sener, with capacities of engineering, construction, operation, and optimization as well, okay? We have a very high, a very flexible supply of hydrogen, okay? Because we're going to supply the hydrogen not only for one use, we're going to use it to decarbonize the combined cycle, okay? Because we will inject part of this hydrogen into the gas turbine, so we will produce green electricity, okay? But we will also provide hydrogen, as you saw in the presentation. We will provide hydrogen for a refuel station, so this is for public transportation, and we will also inject into the pipeline. So the pipeline, it's a facility that is going to distribute the gas very easily, very quick, and in a cheap way to all industrial consumers in the area. Okay, so we have quite a flexibility here to be able to adapt to the different necessities of hydrogen as long as the project advances and we increase the capacity of the plant. I think this is a very flexibility is one of the key features of our project. Okay. At the same time, we're going to accelerate the hydrogen economy, okay? Because since this is not a greenfield project, we're installing this project into an existing combined cycle plant, okay? So this is going to allow us for shorter terms in project construction and as well in shorter terms, okay, for delivering this hydrogen, okay? when we're comparing large hydrogen valley projects, for example, these projects require longer lead times to reach maturity. So this is one of the advantages. Okay, I mean that we are going to give this impulse to the hydrogen economy by shortening the terms and the lead times for the first kilogram of hydrogen produced. Okay, and finally, we're going to count with the most experienced companies here in this project, and well, we really hope that we successfully finish phase 1 in 2022, and we as well are able to continue with the phase 2, which we think it's going to be a great success. Okay. So thanks a lot for your time. We're looking forward to your questions. And for more information, I would recommend you to visit our website, okay, and contact us at any time. Thank you very much.